Hi, everyone. So, of course, I'm Sam. I'm talking to you today about all this, about shipping Rust to people who don't use Rust, or as I like to call it, spreading the glory of Ferris. So two things. I'll be talking about two things, why you might want to do this, why we did this, and also walk you through some of the design decisions that you have to make and the questions that you have to answer while you're doing this. If you want to follow along the slides, there's a QR code or a link up there that you can click and go to. And I'll also be doing some code demos and examples that you can follow along to. So first off, why? Why would you want to do this? Why are we doing this? That is a new, oh, OK. So we at Boundary are building BAML. So we're building a new programming language for calling AI applications. We believe that developers need new primitives for calling into models, and we want those new primitives to be accessible to everyone. So what we have there is you can define types and functions in BAML, and we expose those types all the way through to users in whatever programming language that people want to build their application in, because most people, especially in the AI space, are building their applications in Python, in TypeScript, in Ruby, and Go, and all sorts of other stuff like that. And so we want to provide them with a really good experience and strong types as well, going all the way through to the whole tooling experience of providing things like autocomplete. Naturally, this is a hard problem. We need to build a parser, we need to build a compiler, we need to do diagnostics, we need to provide a runtime. And so that means we need to build on really good foundations. And for us, Rust is that really good foundational layer. It gives us confidence in how to do all of this really hard stuff really effectively, and it gives us the base to build like async, really good errors, and not have to worry about like accidentally having exceptions in the wrong place. There are a lot of different approaches you can take to do something like this, right? We could implement the language 4 different times, once for each language, and just implement it natively in Python, in TypeScript, in Ruby, and Go. We could have done this as a C or C++ core that we then exposed for FFI bindings. We could have done a subprocess approach and exposed everything through IPC or RPC interfaces. And we actually started with a slightly different approach. Originally, like a lot of it was just in pure Python originally. But this today is the approach that we landed on, of having the core logic, everything from the compiler, the error diagnostics, the runtime, and putting all of that in Rust, and then using thin FFI foreign function interface shims and exposing those to users, and having a bunch of glue code that enables people to call into the Rust core. Importantly, one thing I want to call out here is that we're a very small team. We're 6 people. We've done about 150,000 lines of Rust over the past 1.5, maybe 2 years, depending on how you count it. And of the 6 of us, 3 of us did not know Rust 2 years ago. This project, the extent and scope of what we've built, would not have been possible, certainly not with the level of quality that we've done, without Rust. That being said, if you want to do something like this, if you want to create foundational software for people in other languages, it's not all roses. There are problems that you'll run into along the way. And generally, they fall into the category of complexity. And that complexity surfaces in 2 different forms. One is complexity for your users, and the other is complexity for yourself. If you implement a Python library in a language that isn't Python, this is harder. There are things you have to do. We've run into issues with probably every single language that have required our users to spend time with us and go really deep on debugging exactly what's going wrong. We've had interactions with the Python global interpreter lock, with the TypeScript bundler, with Node.js loaders. Go has its own download mechanism, et cetera. Similarly, internally, we have to spend a lot more effort on the tool chain and actually building everything. Because in Python world, if you want to ship Python code to your users, it is essentially just like take a directory of Python source code, bundle it into a zip file, upload it to the package index, and that's it. If you want to test in a Linux container, you just copy it across the boundary. Doing this on a Mac host with like a Linux guest in a Docker VM, you have to do a cross-compile cycle. And that complexity manifests throughout the build cycle, right? You deal with a whole lot of like really arcane error messages. Since we're doing 4 different targets with 6 different architectures each, that's 24 different builds we have to do. So CI is also a lot more complicated. Overall, though, for us, it's very much been worth it. Regressions are really rare, and type safety works. When we get the modeling of the problem correct in our own type system, we haven't really seen a lot of bugs. The bugs usually show up when we get the modeling for a problem wrong, or when something in the external world changes out from under us, like OpenAI starts responding with a new field in their response, or they change the content of a field, and we're like, wait, that's not there. That wasn't supposed to be there. Cargo is a really great build system foundation. For us, that's really, really key. Because we have so many different build processes that we need to work with, and we need to do cross-compilation for a lot of different things. And Cargo and Build.rs have been a really powerful and flexible foundation for us to work with. I am very, very glad that I have not had to touch a CMake list.txt file in many, many years. And the last thing I want to call is that the ecosystems are actually really strong here. Tool chains can actually work out of the box. That screenshot there on the right side, that is literally the first Slack message I sent after I created the first GitHub workflow and pushed it to GitHub to try to release our Python package, because everything built out of the box. I don't know about you, but every single other time I have tried to cross-compile software for multiple architectures, it usually involves at least a few cycles of round-tripping between GitHub and my Git push cycle, but somehow, like, the PyO3 ecosystem and the mature maintainer, I am in awe of you, Messence, whoever you are, maybe you're here. But it worked out of the box, and that was an unbelievable moment for me. Documentation is pretty good. PyO3, NAPI, I'll flip back a few slides. PyO3 is the interface for Python. NAPI is the interface for TypeScript. Magnus for Ruby. And we're using libc and cbindgen for Go, because Go does not make FFI very easy. But there's a lot of documentation out there. And when the documentation stops being sufficient, you can go into the GitHub issues. You can find the maintainers. And there's also a lot of prior art out there. You can go and find projects like Prisma, TypeScript ORM, UV and Rough for the folks at Astral are building a lot of Rust-based tooling for Python users. The folks at Dino are doing this for TypeScript users. A lot of people building on Wasm. A lot of Temporal's core SDK stuff is in Rust. So there's a lot of prior art in the ecosystem at this point that allows people that are following along and trying to replicate this journey to look up existing patterns and find out what has worked for people and what are people actually using in production versus the patterns that might just be in documentation and don't capture all the complexity that you really have to deal with in a real code base. Now, that all being said, there are a bunch of design decisions that you have to make along the way. And that's what I'm going to be spending the rest of the talk going over. So first off, is what kind of API do you give your users? If you give them a simple method call, do you want to force them to work with pure Python objects, or do you want those Python objects to be implemented in Rust? And I'll show you in a second exactly what this means, but there's a couple of things that you want to consider in this process. Things about how hard is it going to be for your users to learn the API, how well do your types integrate with the rest of the ecosystem, and performance implications of crossing the Rust-Python boundary. So to make this a little more concrete, I have this method here. It's in Rust, right? It's pretty simple. It makes a bunch of lorem ipsum placeholder text. It takes an options struct that has 3 fields on it: repeat, crab emoji, new lines, just like how many times you repeat, whether or not you show a crab emoji, and versus new lines. And this is pretty simple, right? And I can expose this through Rust into Python pretty effectively. I can just do uv run, basic demo, and it works, right? We have Python code calling into Rust, and I have a whole bunch of things just working out of the gate. I have a constructor. I have a documentation string for my constructor. I have cross references and highlights for it. I can have doc strings for all of my other stuff, and this works fine for this case. It is also possible to do something like this, where instead of doing that, you do this. And instead of doing it as a Rust-backed object, you do it as a Python-backed object. So here I'm passing in Python options object, which is a class defined in Python. And this, from the user's perspective, looks very, very similar. So why might you want to do this? It feels better. We're Rust people. We want to do as much stuff in Rust as possible. Why would I do this a different way? And the answer is that you have to remember that when you're doing a foreign library like this, you want to design for your users, and you really, really want to prioritize the ergonomics for your users, or at least if you're willing to trade off ergonomics of your library, you need to consider what kinds of errors or other scenario or integrations, other expectations your users have of your library. So let's take this example, right? Our options struct is, again, pretty simple. We have 3 fields on it. Repeat, that's a number. How many times we're going to repeat the string. Crab emoji, a bool. New line's a bool. And let's say our users decide they want to load it from a JSON file. And we'll just pretend it's a JSON string to make things easier for now. So let's say UV run, basic error demo. And this works, this works just fine. Now, if I modify this code, and I now make this unparsable because I'm only passing in 1 field in a struct that expects 3 fields, I'm going to get an error. I'm going to get this runtime error, missing field, repeat. And for those of us in Rust land, this is a normal error. This is an error we understand because we've all used Serde. We understand what Serde errors look like. However, this is not the error that a Python user expects. What a Python user is going to expect to see is this. Whoop. Sorry. They expect to actually parse it. And this is what they expect to see, right? They expect to see an error that says, OK, here's a pedantic validation error. There is a field repeat that is required on the object. It's missing from the input value. And the input value was new lines true and a dict. Also expected crab emoji to be a required field. And it's missing from the input of new lines true. And this is a very, very different error than the Serde JSON error that we as Rust users expect to see. And so you can imagine for a Python application developer who knows Python, who knows what their errors look like, if they see the Serde error, they're just going to be really, really confused. In a similar vein, there are going to be other ecosystem integrations that will go sideways. So for example, if, say, like make lorem ipsum, if my method to make this placeholder text is actually surprisingly compute intensive, and my Python user says, like, OK, I want to run this in a separate process, they might try to do this. They might try to create the options object in the main process, ask in separate process to run make lorem ipsum and pass the options object over. And then what will happen is this. And you get another error, cannot pickle built-ins.rust options object. Surprise. And these are just some of the things that can go wrong when you're dealing with, when you decide to make your users work with Python objects that you've implemented in Rust. And this is not to say that these problems are intractable. It is entirely possible to go and implement the necessary functionality in Rust that will cover all this functionality your Python users just expect to exist in your types. But the point is that this is additional work that you are going to have to do as a maintainer of a Rust library. And if you have the option, if like performance, for example, is not a super critical requirement for a given method, you should seriously consider trying to use more native constructs in the language because you'll get more things out of the box. In a similar vein to trying to be more ergonomic about objects, the way that lifetimes work for your users, or the way that you should design the lifetimes in your library, is very different, right? When we're in Rust, part of the reason that we design our libraries to have lifetimes is because those lifetimes are not only information that the compiler and borrow checker use to verify our own code, but because it's a signal that your users can rely on when they are compiling their code, when they're running the borrow checker on their code, because having lifetimes in our signatures will allow the borrow checker to tell your users, the users of your library, whether or not they're using your code correctly. By contrast, for Python, TypeScript, Ruby, Go users, they don't have a borrow checker that runs on their code. There's nothing that's going to tell them, hey, you passed an object into the library. That object is now invalidated. So to make an example of this, we'll take async streaming as an example. So let's say that we want to make it possible for our Python users to fetch an HTTP stream, right? We want them to be able to make a single request out to some URL, in this case ssc.dev/test, and we're going to get back a stream of HTTP responses, which is a very asynchronous thing. And we want our users to be able to just async iterate over that. Now, the naive way you might do this is you could say, like, OK, I'm going to implement my Python. I'm going to implement a Python object in Rust. That object is going to wrap an actual Rust stream object. And what anext is going to do, and this is the Python async iterator protocol, is that it's going to actually try to pull off the stream and send it across the FFI boundary back to Python. The problem is with this approach is you immediately run into like one of the classic async errors. Borrowed data escapes outside a method, right? And for those of us that have spent time in the async world, this is a pretty familiar problem. Because what's happening is that the lifetime of the stream object has no way of being statically coupled to the lifetime of the future that we're sending back to Python. And you could solve this by with the classic like slap an arc mutex on it. You could do stuff with like copying data around and using broadcast channels, for example. But in both cases, you're doing stuff that like you feel like in Rust you shouldn't really have to do. And so another option that you have in this world is that you have to remember that you're not writing for a Rust user. You're writing for a Python user. And so what you can do is you can use a more native Python construct where you expose an async iterator to your users, and you say, like, OK, I'm just going to give you like the run-of-the-mill like Python async generator. You get a queue, and I will do something with a callback. And under the hood, there's also singletons involved. So callbacks and singletons are kind of the magic glue going on here. And I'm just going to send stuff across. I'm just going to use that callback to transfer data in the FFI layer from Rust into Python and not try to re-implement like core internal Python interfaces in Rust. And what that ends up looking like is this. And I realize this is a lot of code for a single slide, so bear with me for a second. But we have callback-driven stream. We take the URL. We take a reference to the callback. We do some Pyo3 lifetime stuff to pass it in. And then we can grab the singleton Tokyo runtime and spawn a future on it. And then we can create the stream on the stack of that future. And this is really important, right? This is the part that allows us to not have to like wrap the stream in an arc mutex or copy it around, because we can pin the stream to the stack of that future. Once you do this, you can then just grab the Python GIL every single time an event comes in on the stream, and then send it across the Python. And now what we're essentially doing, and I've clicked on the wrong tab, now essentially what we're doing is we're treating the Python queue as our Rust channel. And so now, in this scenario, you have a working stream crossing an FFI boundary. Because you've and async streams, right, are one of those like hideously hard things to do, because not only do you have a single async, you have a lot of asyncs crossing the boundary. And normally, there's a lot of very tricky lifetime management because you're crossing those boundaries. If you try to do this more raw, you'd also run into a whole host of native issues around how to actually bridge the event loops together. And you end up digging into some very deep Pyo3 async implementation details that kind of end up not being possible. And one thing I want to be clear about is that this isn't necessarily the best way to do things, but this is another option you have in your toolkit. When you're building for Python users, you can write Python code to help solve that problem while still keeping the vast majority of your core logic in Rust. And so that's the point of that like if your Python users don't care about your lifetimes, you don't need to encode those lifetimes precisely in your API to make things work for them. And lastly, doing software like this isn't just about like how you write the code. It's also about thinking about the software lifecycles, and specifically how you ship releases to your users. So one problem that you run into when you're shipping multiple versions or multiple distributions of your Rust library to users in different ecosystems is you have this versioning question, right? OK, we could version the Python version and the Typescript version and the Ruby version and the Go version independently of each other, so that way, like, if we want to make a Python-specific fix, we can bump the Python version. If we want to ship a TypeScript-only fix, we only bump the TypeScript version. On the other end of the spectrum, you could just ship all of them in lockstep, and you say, like, OK, anytime we make a change to one of them and we want to bump that version, we bump all the versions simultaneously. And it's kind of hard at first glance to decide where you want to land on. We spent a while talking about this when we were deciding, like 1.5 years ago, like where on the spectrum we were going to land. And we ended up making the decision that we were going to take the easy way out and just version everything synchronously. And 1.5 years later, I am really, really happy with this decision, because it means that we've never gotten confused when we're mapping the version a user is on into our internal version. If you keep the same thing everywhere and you don't have to do any kind of mental translation when you're copying numbers around, like copying a number from like a user's GitHub issue into Slack, or like a Discord message or a text message, and you can just say like, okay, a user came to me and like told me like they had an issue on BAML 0.205.0, I can just like go and tell the team like, hey, we have an issue in 0.205.0, and I don't need to know exactly like which version of the Python package that you're on. I can just say like, okay, some things are on 205.0, that's the version we're going to look at. And it's easy. It's easy to communicate when you don't have to do any kind of translation of numbers. And that's it. If you want to take a look at what we've actually built, you can go check out our actual repo there, github.com, BoundaryML/BAML. If this is interesting to you, or if this sounds like something you would use, or if this sounds like something you'd be interested in working on, of course, we're also hiring. And you can email us at founders@boundaryml.com. Thanks.
All right, we've got time for some questions. If you want to come up to the mic and ask your question, you can come in line.
Hi. I've worked on an API and the Node.js interface. Have you encountered any performance issues with serializing data across that boundary? Because I wrote something that I thought was being very smart about writing it in Rust, and then it made it 4 times slower because serializing it took that much longer than the simpler thing.
So fortunately for our use case, we're not super heavily bound on I/O bandwidth. Our primary source of latency is network latency because we are providing abstractions around like LLM calls, which are incredibly slow. I do know that Prisma, the TypeScript ORM, is actually moving away from this. And I think some of that is just due to very fundamentally intractable problems, because users in Node.js and TypeScript want to work with like Node.js TypeScript objects. And if you're converting it from a Rust internal representation to a Node object representation, that's a move that has to happen. That's possibly a copy that has to happen. And so there's a lot of just like very I/O heavy workload there. But I am happy to say that, at least for our use case, we have not noticed any serious performance penalties there. So thank you very much for your work.
Hi. Sorry, when you're talking about like objects implemented in Rust versus objects implemented in Python, is that like the objects implemented in Python, is that like Python glue code that you have to write manually, or is that something that PyO3 takes care of for
So
you?
PyO3 will take care of this for you. So flipping back to my basic demo, so this Rust options object, calling this constructor will literally call this Rust function, which is annotated with Rust options object new. And so like under the hood, when Python calls this constructor method, it's actually calling this Rust method and like doing this. And then PyO3 is generating a whole bunch of glue code to make it possible for Python codes to just treat this as like a Python function call.
What about Python options object?
Python options object is like native Python code, and the other method that I'm calling here, make lorem from Python, is actually going through like a separate extraction step. And there's other PyO3 glue code that is going on there in the background to handle that translation. So that is like slightly more expensive performance-wise. But again, like for our purpose, this is perfectly acceptable. Like the thing that we prioritize is user ergonomics, as opposed to like being in a super performance critical like tight loop.
Hey there. I'm kind of interested in how you bridged the stream to the generator. Is there like somewhere I could look at this demo and sit down with it, or a blog post or something like that?
Yeah. If you take a look in the Discord channel, or I'll flip back to the slides if I can figure out how to actually do that. That QR code right there, you can scan it, and it'll have a link to the slides and also the repo where I have the demo code.
Thank you.
Absolutely.
Yeah, I have to build a multi-platform SDK right now, or multi-language SDK, and I wonder with the version numbers, if you ever had a problem with when you had to update just the wrapper, or if that was enough when you just waited for the next update of the core.
We really just wait for the next update. It feels a little bad. It definitely feels bad when you're making the decision. Like when you're deciding on the versioning scheme and like asking this question to yourself before you have it, it feels like I should be able to like bump the Python version without bumping the others. In practice, it hasn't really happened to us super frequently that we've had to do that. And it does happen every now and then. But the simplification that it provides to us when we're communicating with our users is just such a big win that I can't imagine doing it any other way unless we actually needed to. If we were in a different world where like we were shipping like glibc versions and we needed like multi-year compatibility across versions, the story would probably be a bit different, but we'll deal with that when we get there.
Yeah, thank you.
I was wondering if you could talk about the cost or non-cost of actually deploying many versions to all these different package managers in different languages, and if that's something that's a big overhead for your team or if it's more of a non-issue.
Do you mean human costs, software build time cost?
Human costs primarily,
okay.
Yeah.
Human cost is not super high. I would say it's a fair amount of work on initial setup. I will say the Ruby toolchain in particular is time-consuming and expensive because it roughly, in order from largest community of users to smallest community of users, it is PyO3, NAPI, Magnus. And Magnus, unfortunately, sits because there's so fewer users. That one is a bit more work to do, but we haven't really had to touch it. The only time we've had to go back and like really handle it was when like CentOS had some like image deprecation like deep in the toolchain stack. And like that was like half a day of work to fix. And beyond that, things have worked. This is one of the things I will say is impressive about the Rust ecosystem, that like a lot of the tooling that we have been able to take advantage of tends to work. I will say there is one slight flip side to this, which is that like none of the FFI providers really have like years-long stability horizons. All of them have shipped like major internal API changes that users will then have to update their thing on. Like in the past like 1.5 years, like we've seen PyO3 go through, I think 2 substantial changes to like the way that they model the lifetime of the Python GIL. NAPI just went from version 2 to 3 like a month or 2 ago, and we still haven't picked that up yet. We do have a PR incoming for it, and Ruby is a separate story. Looks like I got to all the questions.
Going once, going twice. Nobody else has any questions? All right, please give Sam a massive hand.